Hello, everyone. Good afternoon. Hope you all are having good readment. Welcome to Essential Strategies for Kubernetes Adoption. As we were thinking on what we can talk about, right? Whenever you adopt a technology, especially a technology that's going to end up being a fundamental portion of your stack, there are many interconnecting elements. There's the culture, which plays a big part, the organizational structure, the processes you want to set up to empower your teams, and the tools you want to provide the teams to be successful. And most importantly, the architecture, understanding the failure modes of the dependency you're taking, and the architecture you want to design with the failure modes in question. All of these together form your strategy. My name is Ishwar Bala. I'm a director for EKS. And portion of my job is thinking about the culture, the structure I want to set for the EKS service team, and the processes we want to set forward. And I'm passionate about them. I'm joined by my co-presenter, Rick Sostheim, who's the expert in our service team, right? He's going to talk to you about the architecture, the failure modes, and what you want to do to be successful. So we'll split this talk into two portions. I'll cover the aspects with regards to culture and organizational structures and tools and processes, and Rick will take over the next set. And I want to start with setting the context here, right? Let's talk about culture a little bit. This is from the dictionary, and emphasis is mine here, right? It's about the beliefs and ideals you have, and most importantly, enabling your beliefs and ideals to be transmitted on to the next set of people that come onto your team and to your company at the end of the day, right? The transmission part is extremely important when you set up aspects that control your culture at the end of the day. And that's where mechanisms come in, right? Invariably, you're going to have problems, business challenges, technical challenges, and these problems recur at the end of the day. And you want to figure out solutions that enable you to solve these problems in a sustainable way, the right way, sustainable way, and also scale as your team and your company scales. And again, I'll emphasize the sustaining part here, right? Because that's what at the end of the day defines your culture. And I'll speak more about mechanisms. And there are many, many examples inside Amazon that we leverage mechanisms very, very deeply. We do our operational reviews. That's an example for a mechanism. Correction of errors that we do to learn from failures. And even our product development has a mechanism in place. And PRFAQ, you must have heard about the press release, frequently asked questions on how we draft our product specification documents, is another example of mechanism. Now, how does mechanism look in practice? In essence, mechanism is a complete process, right? To the right, you always start with some challenge. A business challenge, it could be a technical challenge. And you're basically wanting to start with the outcomes you want to achieve in order to solve that particular challenge. And you want to identify the inputs that you want to transform into the outputs or the outcomes you want to get to. And the way you do it is the really important part of the mechanism is the one at the center. You want to design a tool that lets you transform these inputs into the outputs or the outcomes and enables you to solve the challenge. And once you design a tool, you got to worry about how do you get it to sustain? How do you get it to adopt first and then sustain? You want to worry about who are your team, is this tool going to be adopted by your immediate team? Or is more teams involved in this equation? What are they going to be concerned about? How do you convince them? How do you make it easier for them to adopt? And once you have the team's buy-in in adopting this particular tool, you really want to set an inspection process in place, right? Is the tool doing what it's intended to do? Are we gaining the benefits we thought we will gain out of this? And are we actually going towards the outcome that we actually set up the mechanism in place for? And you're going to iterate on it, right? You're going to learn that it's working to a particular extent, and it's not completely getting you what you want, and you continue iterating on it. And mechanisms are composed of a number of organizational levers at the end of the day. And if you look at this set of organizational levers, these are intentionally set up in a particular order. The ones at the top are really big levers. Big levers end up driving a lot more impact, really broad impact across your team, across your organization, even across your company. And bigger levers come with a lot of resistance to pull. And you want to keep that in mind, right? And it's only natural to have a lot of resistance because you're actually impacting a ton of teams with that lever. And a good example for a mental model is the customer obsession leadership principle in Amazon. It's a mental model that drives our culture day in and day out, not just in the products we ship, even in the architecture we take on, even in where to invest our critical engineers' resources, engineering time at the end of the day. And with the wrong mental model, you will not build the right mechanism. And with customer obsession being a mental model, right? If we had a different mental model in place of customer obsession, our products and how we engage with customers would be completely different. And right at the bottom is resource. And that's a smaller lever, easier to pull. And for example, right, if there's a new hire joining a company, many companies actually give a lot of things when the new hire joins. Could be a bag that you get to keep your laptop that you got from the company. Could be a cap, could be functional, could be fun. And it's easier to change this lever, right? Because you're not going to see a lot of resistance, and it has a relatively smaller impact. But at the end of the day, in order for you to actually execute on a mechanism, it's always a combination of levers you want to pull. And you can decide to pull a set of levers, and you can also pull them at different times at the end of the day. So I'll be talking more about mechanisms, actual practical examples of mechanisms a little later, but I want to cover the organizational structure aspect a little bit. And I want to talk about how we do it in Amazon. And a lot of this applies to outside of Amazon as well. In Amazon, we tend to build our teams really, really small. And we call them two-pizza teams because the mental model here is like you want to be able to feed the entire team with just 2 pizzas. And in terms of numbers, it's somewhere less than 10, ideally 6 to 8 people in a team. And the reason why we set up a small team is basically in order to give a ton of ownership and autonomy. Ownership and autonomy are two sides of the same coin at the end of the day. One doesn't exist without the other. It's a set of dedicated people who are focusing on a particular business problem, a domain, day in and day out as part of their work, and go solve them, right, with complete autonomy. You want the decision-making to actually end up with the team so that they can actually deliver, iterate faster. And every organizational structure comes with trade-offs and also biases towards certain characteristics. And spoiler alert, at Amazon, we bias towards velocity of decision-making and delivering customer value and iterating on it over and over and over. And with the autonomy and the ownership, we also strongly believe that this lowers the cost of experimentation. You put out a feature out, you put out a product or a service out, you learn quickly whether it works or not. If it doesn't work, go back to the drawing board, make it better, right? And because the decisions are made by the team, they are the complete single-threaded owner, they're more willing to experiment and fail and learn from the failures at the end of the day. So how does two-pizza teams work in practice? Success, like all of us want success in the products that we work in, right? And success inevitably brings more investment into your team. Your team grows, which is awesome. But you really want to be mindful of how much you let your team grow at the end of the day. The growth brings the problem that we tried to solve with setting up a two-pizza team to begin with. Your communication lines are really larger, right? Everybody needs to talk to everybody to make a decision, and the decision-making slows down, ownership falls, and you want to avoid these problems. And for me, when a team grows to a size 12, it's actually time to ask deeper questions. Are we at a place where we want to think about splitting the team? Are we solving too many problems with a single two-pizza team? And go intentionally split these teams. You've got to begin the process of mitosis at the end of the day to split them and make them smaller two-pizza teams. And now, if you proceed further, you end up with a large number of two-pizza teams. And that brings another set of problems. You're going to have deduplications at the end of the day. Remember, we bias towards velocity. There's more ownership and autonomy. Every team wants to solve their problems in a way that enables them to run fast, which results in deduplication at the end of the day. And it's okay. You might want to live with duplication. You might want to run with the duplication so that you can actually get better velocity, and have faith that you're going to resolve the duplication sometime in the future. And the next set of problems that comes with large number of two-pizza teams is inconsistency in operational standards. Each team is going to have their own subculture of how the operational hygiene is, what kind of tooling they use, and that's going to diverge as time goes at the end of the day. And you want to solve for that more importantly. Deduplication you can go solve a little later, but you want to bring consistency, operational hygiene, and standards and tools that apply to all these teams effectively. I want to spend a little bit of time on the AWS operational culture. At AWS, we don't tend to build teams that are like QA specific. There's no operations team. We have a strong emphasis on if you build it, you operate it. And we strongly believe that we build better products because we feel the ownership that we are the ones operating the service, and we're going to learn from the failures. And the engineers who write the service are actually on call, monitoring the service, learning from the failures, and folding the learnings back into the service. And it's one of our cornerstones of our operational hygiene. And everybody in the team has some sort of operational responsibility. Remember, we're not very prescriptive on what a two-pizza team is. A two-pizza team might be just made of engineers. It could be made of product manager and engineering manager and engineers at the end of the day, right? But we make sure that everybody in the two-pizza team has operational responsibility. For example, the managers in the management chain is during an operational incident is responsible for incident management, delivering the right message to the customers, giving them updates on how the recovery is going, and enabling the coordination between different teams if it comes down to engaging multiple teams to solve a particular operational problem. Right? Now, obviously, the engineers are in the tech call, troubleshooting the issue, figuring out what the mitigation is, how we are going to actually solve the problem at hand. And more importantly, we emphasize on learning from the failures. Failures happen, and we have to learn from every failure we have so that we can actually prevent the recurrence of the failure. And one of the most important mechanisms we have in Amazon is correction of errors. It is the mechanism that enables us to learn from failures. It doesn't matter. This is a very generic mechanism. It could be applied to any sort of failure. Failure can be you delivered on a wrong product. You delivered a feature that didn't work with another service correctly. It could be an outage in your service. It could be a business process that failed. Every one of these could be covered by correction of errors process. And I want to talk a little bit about how it applies on the technical side. Again, you see the loop repeating over and over, right? I want to emphasize on the mechanistic part and how the loop is important for it to be a complete and effective process. When you build the team builds a service, a feature, puts it into production, and inevitably outages happen. And it's important that we learn from these outages and think really hard about the actions we need to take to correct this, to prevent further recurrence. And that's what we do with the correction of errors process. And when we fold it back into the service, the team that's building into it, our service gets better inevitably. And in practice, here's how it looks, right? So you have the tool here is about talking about the background, how the impact for a customer during an outage is. It has metrics and data that speaks to the impact. It has the triggering root cause that actually caused the impact, and 5 whys that actually drills down deeper from proximate causes down to the actual root cause. And it also talks about how did we do in terms of incident management. Did we recover correctly? Did we mitigate it quicker, even though we might not have actually fixed the bug right during the operational incident? Did we get to a place where customers are no longer impacted? And all these lessons learned and action items taken are part of the COE mechanism. So COE helps you learn from failures and helps you take corrective actions. And we also make sure that the COEs are read by many, many service teams. We bring it to a central AWS operational meeting, and many teams have an opportunity to read it and learn from it as well. Is that enough? It's not, because you leave it to good intentions again. The place where it fails is whenever a team builds a service or builds a feature, we leave it to good intentions to go back to the COE repository, look at all the action items that might matter to them. So you have a discovery problem. So maybe you fix it by good discovery search tool. But that still leaves it to the service teams to go do that action, pick up all the action items, make sure that their service is designed and architected to not fail. And you don't want to leave it to good intentions at the end of the day. So that's where the operational readiness review mechanism comes into the picture. This particular mechanism distills all the learnings we've had from the availability incidents and folds it into a set of questions that service teams are subjected to answer whenever they're going to launch a product, launch a feature, launch an enhancement. And it makes them think hard about what are their weaknesses in terms of how they're operating their service, and fix them before their service gets into production, right? And it's a cornerstone of our operational excellence. And in practice, it's going to look like a checklist of questions. It'll even point to the past incidents that have happened because of this particular issue, so that the teams can evaluate whether this incident applies to them. And if you look at the structure of this operational readiness review, there are 3 main categories. And obviously, it could be super granular, but I'm going to cover only the first 3, which is architecture. It talks about what are your dependencies. Do you really understand the dependency failure modes? What have you actually done to overcome these failure modes? Do you have the right capacity, right? Do you have the right quotas and limits? Are you set up for high availability, for example, right? Things of that nature. And the second category is release quality. It makes the service teams think about how good are your tools and your deployment practices? Have you made sure that you have enough capacity, especially during deployment? Have you made sure that you drain your load balancers correctly? Is your pipeline set up properly so that you deploy in waves rather than at a stretch deployment? And the last category is event management. Incidents always happen. Are you ready to tackle an incident when it happens? Do you have your runbooks ready? Do you have the right monitoring and alarming? Do you have the right metrics? And do you have the right rollback strategy? And we have multiple variations of this readiness as well, right? So you get a different review when you're launching a service than a feature, than an enhancement. And the last part that I want to cover here is tooling. It's good that we enable best practices, right? We enable processes to learn from failures and also give them best practices in terms of operational readiness review. But we want to go one step further and make tools available for customers, for our services in our case, right? So that they don't have to do a lot of lift in order to leverage the best practices at the end of the day. And that's where we have a deployment working group that brings all these best practices into the tooling that broadly applies to all the service teams without them having to do a lot of work. And the way we do this is we look at the CI/CD pipeline, right? The practices of the service team, and we look at the pipeline, and the pipeline models all the CI/CD best practices of a service team. And we can learn whether they're deploying in stages, how is their deployment methodology, how is their alarms configured, how is their rollback, right? And we actually run them through a set of rules, right? We audit the pipeline. We take what we audited and feed it into a set of rules, and the rules are basically modeling the best practices at the end of the day. And the rules are going to trigger and come out with a decision that then is fed into the enforcement or the policy engine. And the rule can say that I'm going to send an email to the leadership, like notifying that you've got a miss in your best practice. Or it can actually take a decision to completely block the pipeline so that the team actually has to go resolve the issue before it proceeds to deployment into production. Right? In terms of how it works in practice, all these best practices, you will see the teams leveraging integration and pre-prod testing. We leverage canary, fractional deployments, or even deploying fractionally within a particular stage, write alarms, and even metrics that we automatically can figure out and have anomalies in terms of pre and post deployment. And this helps in implementing the best practices without service teams having to do a lot of work. And remember, right, this is a specific example. The deployment tooling is a specific example on how we apply a mechanism. And the same thing applies to any cross-cutting concern you have in your applications, right? It could be compliance, it could be security, and you can leverage the same methodology here that we apply on the tooling. With that, I'm going to pass on to Rick Sostheim. He's going to talk about the technical and the architectural concerns.
Thanks, Ishwar.
Thank you. Yeah.
Thanks. Appreciate that, Ishwar. I want to reiterate that what Ishwar was saying there, especially around strategy versus culture. I think everybody's heard the saying that culture eats strategy for breakfast. This is a case where it couldn't be more true. Having these high leverage methods or mechanisms built into your processes are incredibly important. But with that, I'm going to take us in a slightly different direction here and start talking about how systems fail and what we can do about it. So I'll start with one of my favorite quotes. A distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. This is Leslie Lamport, pretty famous in the realm of distributed computing. It's the general notion that some system that you may be completely unaware of can break across the world, and all of a sudden you're down and you don't know why. So let's talk about the systems that impact Kubernetes and EKS. So Amazon Elastic Kubernetes Service, easy for me to say, is a regional service for managing Kubernetes. The service is available in every AWS region. It's available in GovCloud, top secret regions, and it's available to run regional, outpost, local zone, wavelength, capacity, anything that's available. The service is exposed as a regional endpoint, and it manages a single tenant Kubernetes cluster. So what I really want you to take away from this is that everything that I'm going to share with these in the following slides is relevant to every cluster that you operate. So every cluster that is running your services, the following is true. So along the top line here, we see a single administrative user. This is typically the person who's going to set up your cluster. The persona is that of maybe a sysadministrator. They're going to use the EKS regional endpoint, and they're going to set up the configuration of your service in the EKS cloud. The bottom line is more of your developers, your CD tooling, your automation systems, and they deal with Kubernetes through the cluster endpoint, which is a network load balancer that we set up for you in front of the cluster. So these are just, I would say, standard practices, but there's nothing preventing developers from talking to the EKS endpoint or administrators from talking to the cluster endpoint. These are just, I would say, typical roles. They're not constraints. So what is the regional endpoint for? Well, the regional endpoint is for, the EKS regional endpoint is for setting up your cluster, creating it, describing it. It's effectively the CRUD operations that you want to apply to your clusters to configure all of the AWS level services running on the cluster. So node pools, I have the create node group up there, add-ons, identity providers, things like that. So to communicate with the cluster itself, you have a different endpoint, the NLB that we set up for you and maintain. And this is to apply CRUD operations to your cluster configuration. Everything that goes into the cluster, including extensions that you might apply to the cluster, like API aggregation, if you want to run webhooks and admission controllers, or if you want to run your own CRDs in the cluster. Okay, so let's talk about how our systems work, and then we're going to get into how they break. So at a very high level, Kubernetes is a control plane and a data plane. Right? The control plane basically embodies the capabilities of the cluster, what you want to configure, whether that's your applications running in it, what we refer to as API objects or Kubernetes resources. That's all lives in the control plane. And then the node is effectively where your applications run. It's the capacity of your cluster, where you're going to have your compute resources. So in reality, we don't ever want one of anything. So typically a control plane is going to be distributed for reliability, durability, availability. And your data plane, your nodes, there's going to be a multitude of them. It's going to be sized to fit whatever the business application needs are for your cluster. Tens, hundreds, even thousands of nodes that provide a robust data plane. So I want to go through a bunch of these here, but I'm not going to go into any real depth on these. There's a ton of great resources out there about any one of these components that you can go into in detail. But everything in blue here is considered part of the Kubernetes control plane. So even the elements on the right-hand side in the node itself, the node agent, these are all part of the Kubernetes control plane. So to start off, the etcd is the distributed consensus database. That's the backing store for all of the data in the cluster. The API server, shown up there just simply API. That's how every other component connects into the cluster. That's how we talk to it. The scheduler is, as you would assume, it schedules your workloads onto the cluster. The CCM, the Cloud Controller Manager, is how your cluster talks to the AWS cloud. And every hosted Kubernetes service has a different one. And then the CM at the bottom, the Controller Manager, also sometimes called the Kubernetes Controller Manager, basically is where all of the controllers live that employ the functionality that you expect from Kubernetes. So pods are really your application. A pod is the delivery mechanism for getting your application scheduled onto the cluster. The scheduler sees that, hey, this node has available resources on it. I'm going to go ahead and schedule pods there. Every time we schedule a pod, it decrements the amount of resources that are available from the node, and it'll continue to do this until it has everything that's waiting scheduling or available to be scheduled in the cluster running in your cluster. And it does so by using the kubeproxy at the bottom there. Kubeproxy works with the kubelet, which works with kubeproxy and containerd to schedule and execute your pod on your node. Okay, so let's zoom in on just the control plane a little bit here. First, let's start with etcd. Since this is our database, this is our node or our cluster local database, and it's a single tenant database, we really don't want there to be a single point of failure. So we run these in multiples. It's a consensus cluster, and consensus loves odd numbers, right? So we have 3 of them. The API server communicates with our etcd cluster, and it runs in an active load balance configuration. So the API server is our primary component for how we interact with our cluster. And then lastly, all of the other components that run on the control plane, we have them configured in an active-passive configuration. Only one of them can be in control at any given time, but we want them to be available so if anything fails, we can click over to it in a heartbeat. Okay, so let's break these components into the infrastructure for deployment as a highly available control plane. So the first thing we want to do is we want to put each member of the etcd cluster in its own instance. Then we want to take everything else that's running on the control plane, And we want to distribute this evenly across the rest of the KCP or the Kubernetes control plane in a matched pair. So active-active or active-passive. We want a duplicate of everything running on multiple instances. If we now extend this to the infrastructure or the actual instances that run it, you see we kind of logically group the top and bottom there, a duplicate of the control plane. We put that behind your network load balancer. Route 53 is updated for you to be able to find it. And then behind the scenes, we have our etcd cluster running in a 3-node cluster for high availability. So this is a little bit of an eye chart, I apologize. But you can see here that this is the infrastructure that we actually deploy behind the scenes to implement your cluster. This is actually a high-level view. If I were to try and put everything in here, it would be much harder to even understand. But basically, the important things here are that etcd at the bottom gets its own auto-scaling group. So we put all of the etcd instances into an ASG and spread them across a minimum of 3 availability zones for durability. If any one of them goes away, it remains highly available. We take the Kubernetes control plane and we put that in its own auto-scaling group and attach an ENI into it, which I'll get into more. And that is in 2 of the availability zones. And if you've ever created your Kubernetes cluster, depending on the tools you use, some of this might be abstracted for you. But those 2 availability zones match the availability zones that we require from you when you create your cluster. So the subnets that you provide, what we want to do is anticipate where you're going to have your capacity running in the cluster, and we want to require that it be diverse. And so we create the Kubernetes control plane instances in the same availability zone as we expect you to run your capacity into. All right, so finally, the top half up there, we've got a whole bunch of networking infrastructure that allows you to run private or public clusters, depending on the accessibility you want for the cluster. It allows you to be able to communicate with the outside world, with your container registries, with your users, with whatever dependencies you have that you need to pull in. And most importantly, it allows you to communicate with the nodes in your data plane. All right, so let's take all of that complexity and shrink it down into one picture. This picture represents everything we just saw. And then we want to get it over here to the side and make room for our data plane. So when EKS first launched in 2018, this was the only way you could manage capacity in your cluster. You could self-manage EC2 instances, bring them up in your VPC, and attach them to your cluster. So you could use any instance type you wanted, but you were responsible for the entire life cycle of the instance. You had to update it if there were patching requirements. You had to, when a new version came out, you had to roll that update. So all of the work responsibility was on you. We introduced managed node groups. So managed node groups affects the same concept. You can still run all of the EC2 capacity in your own VPC, and you can pick any instance types you like, and including spot instances. They're not shown here, but spot instances work equally well. But we're going to take the responsibility for managing the life cycle of it. So we'll update it. It's under your control. You get to trigger when that happens, but we will manage the life cycle of the nodes for you, updating it, and hopefully removing a whole bunch of undifferentiated heavy lifting that you have to do with self-managed. So at the bottom there, you see AWS Fargate. AWS Fargate runs in our VPCs. All the capacity is managed there. And really, it takes away the necessity for you to even think about infrastructure and just allows you to think about your applications and run in a serverless fashion. And then last but not least, we have the newest entry here for capacity management, which is Carpenter. Carpenter is, I would call it an advanced capability management construct. It's not fully managed. You have to install it on your cluster. We're looking at what the future of that looks like. But Carpenter here showed managing EC2 and spot instances as well. So next we're going to venture into how things break. So we established all the components here and what they do. But before we go into that, I really want to stop for a moment and pause on the EKS Best Practices Guide. This is a resource that's managed by EKS's developer advocacy team. It has sections for security, reliability, networking, and it is a tremendous resource. And I'm going to try really hard not to duplicate what they have in here because the guide is phenomenal, stands on its own, and I highly recommend it. They've done a fantastic job with it. So let's talk about how systems fail. More specifically, let's get into how Kubernetes fails, and then we'll talk about EKS. So my goal here, again, is to provide not a duplication of what's in the best practices guide, but to think more at that mental model level that Ishwar was talking about. How we use the kind of these high leverage views. So a lot of what I'm going to talk about could sound very much like best practices and processes. It's not. This is how we think about failure. It's how we think about analyzing systems. It's how we think about making sure that we are operationally in the best state that we can be for running clusters, for running our service. So to start with, let's talk about first the three major failure domains. So we have the EKS service itself, the top left. We have the Kubernetes control plane, the bottom left. And then we have the data plane itself. So those are effectively the three major failure domains. First, let's look at what happens if the EKS service itself fails. Now, we hope it never happens. This is our full-time job is to make sure that EKS stays up and running. And we work really hard at that. But it's code, and it's infrastructure, and it's a bunch of dependencies, and just like Leslie said, some things break, we don't always understand why, and it's going to impact the cluster, or it's going to impact our service. So what does that really mean to you as an end user? Now, I'm showing a bunch of CLI commands here. This could just as easily be commands through an SDK, or CDK, or CloudFormation, or whatever you're using to administer your cluster. But anything that uses the EKS service endpoint could potentially be impaired if there's an outage in the EKS service itself. And those failures are going to usually take the form of returning some error code back to you in the SDK or in the command line. Or in the worst case scenario, they could potentially just time out. So what does this mean to you running an application in a Kubernetes cluster? Well, ideally, it doesn't mean anything, right? Ideally, there's a separation of concerns here that allows your cluster and everything running in it to be completely independent of any failure that's affecting the EKS service itself. So take, for example, API Gateway. API Gateway is the mechanism that EKS uses to expose all of our APIs on the service endpoint. If API Gateway goes down for some reason, we're going to have a bad day. If what's running in your cluster doesn't care about API Gateway, why should you care, right? We don't want to have that correlated failure. We don't want to have our computer that you're not aware of affect your computer. We want to make sure that you continue running, so these remain very highly isolated failure domains. So this is leaning into that mental model that I was referring to, and this is one of the design principles that we strive for in everything we build at AWS, and that's the notion of static stability. So I want to pause here and draw attention to the Amazon Builders Library. If you haven't had a chance to check it out, I strongly recommend it. But I want to start with this definition from Becky and Mike for statically stable designs. In a statically stable design, the overall system keeps working when a dependency becomes impaired. Perhaps the system doesn't see any updated information. However, everything it was doing before the dependency became impaired continues to work. And this is what we strive for. So looking at a really high level here, EKS is broken up into a control plane and a data plane. Our control plane are all of the events, all of the requests, all of the state that we maintain to manage your cluster. The data plane is the entire set of all Kubernetes clusters that we vend. And we want to keep these statically stable and independent from each other. And that's what we strive to do. Okay. So there's still, if the EKS service is down for some reason, there's a bunch of stuff that isn't working. Well, what is it that isn't going to be working? Some subset of the features are not going to, so if you want to spin up a new node group, or you want to add a new add-on, or update that add-on, or add a new identity provider. Depending on the specific failures, the dependencies, it simply may not work at this point in time while the failure is ongoing. So conversely, under a different set of failures, you might want to, I don't know, you may still be able to list clusters, you may still be able to describe things that are taking place or that exist in the service, but you just can't update it. It depends again on what the failure is. Every event has unique characteristics, but there's some things that we can do in a general sense to deal with these failures. So what's the prescriptive thing to do here? Assume that your request has timed out or returned some error code. The very first thing you should do is attempt to retry it. Like, it timed out. Don't assume that it's a persistent failure. Assume it's transient. Assume that there was some glitch, and let's retry that request. Let's see if we can get it to go through the second time. Now, if the failure is persistent for some reason, let's assume for some definition of persistence. Don't just keep hammering away, though. It's fine to retry. Retry is a common mechanism. But we also want to apply some back-off strategy. We want to make sure that we're not just sitting there hammering the service endpoint. So progressively wait a little longer as well. Like, every time we apply some back-off, we also want to introduce some variability into that back-off. So let's say that I'm retrying my request every 60 seconds. If I have tens or hundreds or thousands of things that I'm trying to manage simultaneously, and we're experiencing a widespread outage, then you could be spending, at the top of that minute, you could be sending hundreds or thousands of requests. And so what we want to do is avoid instigating correlated failures. So adding some jitter and distributing those across the minute or whatever that period of time is that you decide is the right upper maximum for your service makes a lot of sense. So with that, I want to go back to, where did it go? I want to go back to the builder's library and talk about timeouts, retries, and back off with jitter. So Mark Brooker, Senior Principal Engineer at AWS, has provided this guidance. AWS has learned a tremendous amount about how to manage systems at any scale. And this article takes you through the nuances of thinking through these, what could seem like very simple assumptions to make and how you operate simple things like retries and backoff. But there are really some nuanced details that you can get into, and Mark does an excellent job of explaining that and how we think about it. All right, so let's say now that the failure moves to the Kubernetes control plane. So this is our primary contract with you, the user of EKS. We stay up at night making sure that the Kubernetes control plane is highly available. This is the thing that we provide an SLA for. So we provide a 99.95% uptime guarantee with financial considerations if we don't meet that SLA. So against all of our best efforts, something happens and the Kubernetes control plane is impaired for some reason. Now what do we do? Well, first and most importantly, this is the static stability principle again. Your application running in the cluster should be just fine. Again, if you don't have a dependency, a direct dependency on the Kubernetes control plane, it shouldn't impair your application. If you're not querying the control plane for updates on different resources, API resources in the cluster, the node itself is going to fail open. So Kubernetes has designed the worker nodes in the cluster to be statically stable. It doesn't mean that it's going to stay up forever, right? It could, but it depends very much on your application, what's running in the cluster. Does it have a dependency on consuming additional CPU or memory, disk space, or network bandwidth? As long as the instance that you're running on can continue to provide those resources, there's nothing preventing from that node from running your application for as long as it takes to recover. So if you have monitoring agents that are embedded in the node, they can continue to report out health status on the node. If you have access enabled, you can SSH into the nodes and see what's going on. Again, if we look at what's available to us and what isn't available to us, now everything that we were using from the API server, all of a sudden we may have impairments here. We may not be able to create new or modify the objects that exist in our cluster. I want to pause here for a moment and talk about the SDK for 1 second. So most of these things, again, you could be using this as a user, logging in, typing kubectl commands, or you could be working against this through an automation system with an SDK. There are numerous SDKs that are available in the world for interfacing with Kubernetes with different language bindings. I would say that the Go language binding is obviously the most mature, and the Java language binding is very closely behind it. But as you get further away from that, as you get into different, less popular, or I wouldn't say popular, but less commonly used libraries in different languages, you may find that the support for all of these best practices is going to vary in implementation in the library. So keep your SDKs up to date. They're constantly being updated. And if you find that the SDK isn't working the way you want it to, most of these are open source, and you can make contributions to it to improve them as well. So something I recommend. But so far, what have we described? If the API isn't available, what do? We retry, back off, and add jitter. Sounds simple, and I'm going to keep boring you to death with it, but that's the best thing you can do. So for whatever reason, there's a persistent failure in the control plane. EKS is aware of it, we're working on it, but you're just not feeling comfortable with the control plane being unavailable. So what can you do? What are the options available to you here? Well, you could, because the service is still up and running, you could spin up another control plane. You could, if you had clusters, or you could create a new cluster, you could scale up existing clusters. The EKS service itself is unaffected by this outage, so we could potentially use that to bring up additional clusters, additional capacity to run our business applications. But there are trade-offs to that, and we'll get into why you may or may not want to do that in a minute. So let's assume that the entire control plane isn't impacted, but maybe it's a partial failure. So in this case, maybe the API server is impacted. Now, the API server, as we already said, is kind of this central component in the control plane that allows everything to talk to etcd. You get a lot of choices about what you want to do with your API server. Obviously, it's where you configure all of your Kubernetes resources. Everything that runs your applications and defines how they operate are in the API server. But you can also install aggregated APIs, CRDs, webhooks, admission controllers, all sorts of things. The main concern with each one of these is operational stability. So if for any reason, like let's say you've installed an admission webhook, and that admission webhook is connecting to a service that's unavailable, and it's not authenticating any requests that are coming in to the API server. Well, you've basically broken all of your ability to process requests through the API server. Or maybe you've found an open source controller that looks interesting to you, and you installed it on your API server, and it's just hammering etcd in a tight loop, just doing unconstrained queries. All of a sudden, your API server is going to be having a really bad day. Now, we constantly monitor the health of etcd. We constantly monitor the health of the Kubernetes control plane instances and the processes running on it, but we can't look inside your cluster. That's your data, belongs to you, hands off for us. So across the board, this looks green to us. We've got this green across the board dashboard internally, but you could be struggling. So what we really want is to think long and hard about the things that we put into our cluster. If we have users that are doing lists or watches of some sort, and they're querying large object data sets, could they be improved? Could they be paginated? Could they be turned into asynchronous calls? If you're doing something that is synchronous, can it be paginated so that it's not going to just put this constant pressure on the API server? All right. So what about things that aren't necessarily your responsibility, but more so our responsibility? etcd. etcd is the one thing that I think most people worry about when they think about running Kubernetes clusters. So if an etcd failure node goes down, The beauty of it being a consensus-based quorum protocol is that the rest of the cluster doesn't care. 2 out of 3 is great. It'll continue to operate. Again, it's statically stable, and it continues to allow updates to your cluster. Everything can continue to operate as intended. What happens if a second node goes down in the etcd cluster? So a quorum database without a quorum is effectively a read-only replica, right? It's still statically stable, you just can't update it. It's in a read-only mode. So everything that was running in the cluster continues to run in the cluster. Nothing should be impaired, everything continues to operate as normal. You just can't do changes to scale, you can't add new pods, you can't launch new things, but you can still query the state of the cluster and everything that was in there should continue to operate. So as soon as these instances recover, as soon as we bring them back, right, the EKS team is immediately made aware of any time anything like this happens. Quite often these auto-remediate. If not, we work this to root cause, but your cluster comes back online, or your etcd member comes back online. It immediately syncs to the leader. It takes the transaction log, applies it, catches up the members, and they continue working. But let's say that the etcd is working just fine. The default storage size for etcd, if you were to just take it off the shelf and run it in your own Kubernetes cluster, is 2 gigabytes. Every EKS cluster that we create runs an etcd cluster with 8 gigabytes of storage built into it. Now, what does that mean to you practically? Well, you can have hundreds of thousands of objects in an EKS cluster with an 8 gigabyte data store without any problem whatsoever. What you don't want to do is use API as the data store for your applications. You don't want to try and push a tremendous amount of data. I've seen people do some things that you wouldn't recommend. I wouldn't recommend it. You know, a bunch of, whether you're encrypting data and sticking it into manifests, whatever you're doing, it's not an ideal practice. It's an anti-pattern. You want to have configuration data in etcd and the objects that represent the Kubernetes resources, but that's about it. So let's say, for example, that you stuff these things full of, I don't know, certificate chains or something like that. The API server can do that. It's just you're going to fill it up, and we're going to send you, again, it looks like it's healthy to us, but you're going to get, all of a sudden you're going to get requests that are failing. So if you're, and this is the one place where I will say, go back to the best practices guide, add monitoring for etcd DB total size if it's something that you're worried about. But let's say all of these guarantees, all these concerns aren't enough. You still want to have a cluster backup, restore, migration strategy. So this is not your application data. This is just the data that exists in the cluster's control plane. So this is just a backup of etcd. So AWS solutions, so we have AWS Managed Services, AWS Professional Services, open source solutions, and there's a bunch of commercial third-party solutions if what you really want is to have that extra level of security at night around your etcd data. So let's go back to our detailed view of the control plane, simplify it down to just the elements that interact with etcd. And the E and I's here, this is effectively how we communicate with your cluster. So anytime your cluster needs to, it depends if it's a private or public cluster. If it's a private cluster, the E and I's are going to be the mechanism that your nodes use to communicate with the API server. If it's a public cluster, the data plane is going to communicate over the NLB. And then if it's a outbound connection from the API server into your capacity, then that's going to go over the E and I's. So let's go from infrastructure back to our conceptual model here and look at this in terms of the control plane and the API server and the nodes. So what if one of your nodes fails? Now, given how we've talked about how EKS thinks about capacity or failures in our mental model, so this should be statically stable, right? So if all the pods that are running on this node all of a sudden fail, what's that going to mean to your application? Well, ideally, what we want to do is use Kubernetes itself to give us the right constructs to provide that active-active load balance configuration, which we would think of as being a statically stable design. So Kubernetes is, if nothing else, a system for democratizing distributed systems patterns. And that's effectively what this is. We've set up a group of objects that are working together in your application behind a Kubernetes service load balancer, and it's running as an active-active. Now, if I wanted to, I could just as easily make this active-passive by adding a lease object where only the active member is updating the lease, and if for any reason it ever dies, it's not going to update the lease, and one of the other members is going to take over and become active, and the others will remain passive. So there's an interesting class of failures that can happen if instead of the node failing, it just becomes disconnected, network disconnected for some reason. All of a sudden, the Kubernetes control plane starts after a sufficiently long period of time. It thinks that that node is dead. And so the pods that are running on the node, if they're part of a higher level construct, are going to get rebalanced into the rest of the cluster somewhere. If they're part of a deployment, if they're part of a replica set, they're going to get rebalanced into the cluster. When that node comes back, everything that was running on it, and again, if it was network disconnected but not failed, everything that was running on it is going to get terminated. So you have to think in terms of preparing for that. What happens if I'm on a node that suffers a network disconnect and then comes back? Those pods are going to get descheduled. They're going to get removed. The node's going to go back to a ready state, rejoin the cluster, be reinitialized, and the scheduler is going to start looking to put new pods running on it. So depending on the higher level construct you're using, whether it's a daemon set, a replica set, a deployment, each one of these has semantics built into it. And the important thing is just to understand those semantics, how they work on a type-by-type basis. Okay, so what if the impairment is actually to the control plane? So going back to our static stability mental model, ideally, if this were ever to happen, there would be no impact to your application. Again, everything's going to fail open. Your application doesn't rely on the control plane. You've built a statically stable application that's independent of the failure of the control plane. In reality, we've been looking at these things in isolation, but typically there are tens, hundreds, thousands of nodes in our cluster. So it's really important to know that, one, as your cluster grows, we scale up those control plane instances so that they can deal with failures as well. And two, if for some reason, in the worst case scenario, if all of a sudden 1/3 of your cluster were to go away, there's also a 50% chance that half of the control plane is going to go away, depending on what AZ is affected now. Worst case scenario. So it's important, I'm sorry. Yeah. I'm getting lost in my own notes, I apologize. Anyway, in this state, the cluster and everything running on it is still statically stable if we've provisioned sufficient capacity to handle this type of failure. Now, going back to what we talked about earlier, if what we want to do at this point is provision another cluster and start to move capacity over to it, or try and provision an additional capacity in this cluster, we're really not statically stable. Now we're putting pressure on the control plane and the AWS cloud services behind the scenes to bring up additional resources to migrate these to a new cluster, which really isn't, it's at this point, it's very much a business application decision. Is this a critical service that has to be highly available, or can you continue to run in a statically stable but degraded state until it recovers? Maybe you can't or can't afford over provisioning inside your cluster to handle the loss of 1/3 of your application compute. It's very much an application-dependent decision. Fortunately, if we do decide to do that, Kubernetes itself has a lot of retry and back-off mechanisms built into it so that it doesn't overwhelm the control plane itself. But what if we have 5, 10, 25 pods running on every single node in our compute space. When these start to come back up, if they're not well behaved, if they're not employing those retry, jitter, back off and jitter mechanisms, they're going to hammer the control plane. And when they do that, if they're listing large object sets or pulling down data through the Kubernetes API objects, I've seen the control plane take like hours to recover. It entirely depends on what you're doing with it and how, but it can extend a recovery from a few minutes to a few hours. And the service at this point is back up. Everything's running. The Kubernetes control plane is fine, but because we've put so much pressure on the control plane and we're not employing these standard mechanisms to handle these failures, we're just hammering the control plane. So last reference here, the Amazon Builders Library. Joe has an article here about how to avoid overload in distributed systems by putting smaller services in control. There's a limit to what you can and can't do with EKS because of the way it's designed, but there's some really deep thought that goes into this about what the considerations should be about handling overload. So last but not least, some references, resources that we mentioned, the ORR, the COE process that Ishwar made reference to, the Amazon Builders Library, and the EKS Best Practices Guide. I highly recommend all of these resources, and I just want to say thank you. I appreciate